An SQL database is a type of relational database management system that uses structured query (SQL) as its interface for interacting with and manipulating data. In a SQL database, data is stored in tables like spreadsheets with rows and columns. Each row represents a single record, and each column represents a field within the record. They are stored on data storage systems, typically on hard drives or solid-state drives within a separate server. Some popular SQL database examples are MySQL, PostgreSQL, Oracle Database, Microsoft SQL, SQLite, and so on. They are widely used in applications that require complex transactions and are efficient in querying, especially in traditional enterprise apps. Tables are the fundamental building blocks of SQL databases. Similar to a spreadsheet, each table holds data about a specific topic, such as customers, orders, or products. For example, a customers table might have columns for customer ID, name, age, email, and so on. Each column in a table is required to have a specific data type. For example, ID will be an integer, the name is varchar with length of 100, the age is also integer, and the email can also be a varchar of a certain length. And each row in table represents a single record. For example, this query will insert one row in our database table. To connect multiple tables together, we have relationships, which define how tables relate to each other. The most common types are one-to-one, where each row in the table A is linked to one and only one row in table B. We have one-to-many or many-to-one, where a single row in one table can relate to many rows in another table. And we have many-to-many, where rows in table A can relate to multiple rows in table B and vice versa. In order to connect tables together, we first need a primary key, which is a column or set of columns used to uniquely identify each row in a table, meaning it's unique. And we also use foreign keys, which is a column or set of columns in one table that uniquely identifies a row of another table. Basically, it creates a link between two tables. For example, here in orders table, we have customer ID, which is pointing to the ID of customers table. And we also have the products foreign key, which is pointing to the products table's ID. Using primary and foreign keys, we can join our tables, and SQL uses join to combine rows from two or more tables based on the related columns between them. The common types of joins are inner join, left-right joins, and full outer join. For example, if we want to join the orders and customers table, we can do this query where we select orders ID and customers names from the orders table, and we do inner join customers on orders, where order customer ID equals to the customer table's ID. And this type of join will return records with matching values in both tables. If we do the same query but with left join, it will return all records from the table on the left and the matched records from the table on the right. So the inner join fetches only the orders with corresponding customer information, while the left join fetches all orders, including those without corresponding customer information, and the missing values are filled with nulls. And the schema is what defines how the entire database is organized in these tables. It includes tables and the relationships between them, and the structure of each table, like columns and data types. We use it as a blueprint for how data is stored in the database and ensuring that data is organized consistently. And the next important part are indexes, which are special lookup tables that our database search engine can use to speed up the data retrieval. Suppose our example customers table has thousands of rows. We often need to query customers based on their city, which is not the primary key of the table. And in this scenario, an index on the city column can significantly speed up these queries. In case there is no index on the city column, a query to find customers in a specific city, say New York, would require a full table scan, and this is inefficient, especially for large tables. On the other hand, if we create an index on the city column and then the same query is executed, the database now uses the index to quickly find all customers in New York without scanning the entire table. And the difference in performance will be noticeable with large datasets. For small tables, the impact might be very tiny or even negative due to the overhead of maintaining the index. So indexes are improving the query performance. The primary reason for using indexes is to speed up query performance, especially for large tables. Without an index, the database has to perform a full table scan, which is a slow operation for large tables. Indexes can also enforce uniqueness for columns when you want to ensure that no two rows have the same value in certain columns. And they also improve the speed of data retrieval operations by effectively locating and returning the data. They are particularly beneficial for queries involving joins and order by and group by clauses. But they also come with trade-offs. One of them is increased storage. Each index you create consumes additional disk space, and the amount of space that it uses depends on the size of the table and the number and type of columns used in the index. It also adds maintenance overhead. Indexes need to be updated whenever data is inserted, deleted, and updated in the table. And it means that write operations like insert, update, delete can be slower on tables with many indexes. And having too many indexes can make the query optimizer's job harder, potentially leading to suboptimal query plans. Also, indexes are stored separately from the data table, usually in a structure that is optimized for quick search and retrieval. Most indexes are stored in B trees or variations of it like B plus trees, but B trees are the most common data structure used for indexing in SQL databases because they allow for fast lookups, insertions, and deletions. And they also keep the data sorted and allow to do all these operations in logarithmic time. If you're curious what other data structures are used in SQL, they also use hash tables with a hash function to map keys to specific positions in index. In some simple cases, particularly for small tables or temporary workspaces, a database might use a heap structure, and this means that the data is unsorted and inserted wherever there is space. Heaps are fast for insertion, but can be inefficient for queries as they might require a full table scan. For some special use cases, databases might also use types of trees, including binary trees, AVL trees, or red-black trees, and each of them offers different performance characteristics for balancing, searching, and inserting and deleting the data. In some cases, SQL databases use R trees instead of B trees. They are commonly used in geographic information systems and databases that deal with spatial data. And for indexing certain type of string data, they use tries or prefix trees, which can provide efficient means of searching for keys with common prefixes. Now imagine a banking system that uses SQL as a database, and user A wants to deposit some money into user B's account. What happens if they send the money, we take this money out of their account balance, and then suddenly our database crashes? Does this mean that the money that we took out of user A's balance disappeared? Well, not with SQL databases, because they use SQL transactions for these kind of scenarios. Transactions are a sequence of one or more SQL operations performed as a single atomic unit. And the purpose of this is to ensure data consistency in the database. A transaction has the following properties, which are often referred to by the ACID acronym. A stands for the atomicity, which means that the entire transaction is treated as a single unit, which either completely succeeds or completely fails. C stands for consistency, which means that transaction transforms the database from one valid state to another valid state. Isolation ensures that modifications made by concurrent transactions are isolated from one another until they are committed. And durability ensures that once a transaction has been committed, it remains there even in the event of a system failure. The key commands in SQL transactions are begin transaction, which marks the starting point of an explicit transaction. Next, we can commit the transaction, which will save all the changes made during the transaction to the database. And in case one step of the transaction failed, we can do a rollback that will revert all the changes made during the transaction and returning the database to its state at the beginning of the transaction. In our example, where we need to transfer, let's say, $100 from account A to account B, will involve two steps, deducting the amount from account A and adding it to account B. And both steps need to be completed for the transaction to be successful. Here is how the SQL transaction would look like. We start by doing begin transaction to ensure the following operations are part of a single atomic process. Then we deduct $100 from account A, and next we check if the account has sufficient funds. If the account doesn't have enough money, the transaction is rolled back using rollback transaction and canceling all changes. Otherwise, if account A has enough money, then the $100 is added to the account B. And in case both updates are successful, only then we commit the transaction, which is executed to permanently apply the changes made during the transaction to the database. This will ensure that both accounts are updated appropriately, and if there is an issue at any point, none of the changes are applied, maintaining the integrity of the data. We also have isolation layers in database transactions, which determine how transaction integrity is maintained and to what extent each transaction is isolated from one another. The first layer is read uncommitted, which is the lowest level of isolation. Here, transactions can see changes made by other transactions even before they are committed. So in our example, if we are transferring money and another transaction is updating the balance of account A or B, this transaction might read these uncommitted values, and it can lead to issues like seeing a balance that doesn't actually exist. Next layer is read committed, which ensures that a transaction can only read data that has been committed. This level will avoid the issues of read uncommitted by ensuring that only committed balances of account A and B are read. However, if the balance is read multiple times within the transaction, it might see different values if other transactions are modifying it. That's why we have the next layer, which is repeatable read. It ensures that if a transaction reads data a second time, it will find the same data values. This level will prevent the transaction from seeing changes made by others between multiple reads of the same data within the transaction. However, it might not prevent phantom reads, and for that we have serializable level. It is the highest level of isolation. Here transactions are completely isolated from each other, as if they are executed serially. This will ensure complete isolation. No other transactions can interfere with the transfer process, and it prevents all concurrent issues, but it adds the cost of reduced concurrency and potential performance issues due to locking. And with different isolation layers, several phenomena can occur. The first one is being dirty reads. A dirty read can occur when a transaction reads data that has been written by a concurrent uncommitted transaction. For example, if the first transaction starts and transfers some money from account A to B, before transaction 1 is committed, transaction 2 starts and reads the balance of account A. If the first transaction fails and rolls back, the second transaction has read a balance that never was officially committed. Next one is non-repeatable reads. This happens when a row is retrieved twice and the values within the row differ between reads. Essentially, another transaction modifies the row between the two reads. For example, transaction 1 starts and reads the balance of account A, and then transaction 2 transfers $100 from account A to B and commits. And then the first transaction reads the balance of account A again and sees different balance than before. And the last one is phantom read, which occurs when in course of transaction new rows are added by another transaction to the records that are being read. For example, if the first transaction starts a query to count the number of transactions of account A, and then the second one inserts a new transaction record for account A and commits, and then this transaction counts the same number of transactions for account A and finds more transactions than before. And by increasing the isolation layers, we can reduce the types of phenomena, but with the downside of lower concurrency and potential performance impacts. Now let's see how we can scale databases. The first option is vertical scaling or scale up. In vertical scaling, you improve the performance of your database by enhancing the capabilities of individual server where the data is running. This could involve increasing CPU power, adding more RAM, adding faster or more disk storage, or upgrading the network. But there is a maximum limit to the resources you can add to a single machine, and because of that, it's very limited. The next option is horizontal scaling or scale out, which involves adding more machines to the existing pool of resources rather than upgrading a single unit. Databases that support horizontal scaling distribute data across a cluster of machines. This could involve database sharding or data replication. The first option is database sharding, which is distributing different portions, shards of the dataset across multiple servers. This means you split the data into smaller chunks and distribute it across multiple servers. Some of the sharding strategies include range-based sharding, where you distribute data based on the range of a given key, directory-based sharding, which is utilizing a lookup service to direct traffic to the correct database. We also have geographical sharding, which is splitting databases based on geographical locations. And the next horizontal scaling option is data replication. This is keeping copies of data on multiple servers for high availability. We have master-slave replication, which is where you have one master database and several read-only slave databases. Or you can have master-master replication, which is multiple databases that can both read and write. Scaling your database is one thing, but you also want to access it faster, so let's talk about different performance techniques that can help to access your data faster. The most obvious one is caching. Caching isn't just for web servers. Database caching can be done through in-memory databases like Redis. You can use it to cache frequent queries and boost your performance. The next technique is indexing. Indexes are another way to boost the performance of your database. Creating an index for frequently accessed columns will significantly speed up retrieval times. And the next technique is query optimization. You can also consider optimizing queries for fast data access. This includes minimizing joins and using tools like SQL Query Analyzer or Explain Plan to understand your query's performance. In all cases, you should remember the cap theorem, which states that you can only have two of these three: consistency, availability, and partition tolerance. When designing a system, you should prioritize two of these based on the requirements that you have given in the interview. Thanks for watching. For important updates and weekly insights, subscribe to my newsletter and follow me for more content like this. See you next time.